Hello, my name is Victor, and welcome back to another ALINT-PRO tutorial. In today's video, we will be covering dynamic CDC analysis of some complex synchronizers recognized by ALINT-PRO. In the previous video, we covered dynamic CDC analysis of simple synchronizers, and so this will be a continuation to finish off the rest of those synchronizers. So, what we'll do is we'll go ahead and open up the exact same workspace. That's going to be the CDC Synchronizers demo workspace here. And once we open this up, we'll go ahead and make sure that we clean our workspace. And then I'll go ahead and clear our terminal, and then we can go ahead and begin with our first design. So, our first project is going to be the Mux Synchronizer, or the multiplexer synchronizer. And what we can go ahead and do is we can go ahead and check our current directory, and then from there we can go ahead and execute the script, which is going to be the runme_sim.do script. And what this is going to do is it's essentially just going to compile our design and then send it over to Riviera-PRO so that it will handle these simulations. Now once we go ahead and execute this, that'll get going. And in the meantime, we are going to take a look at the CDC assertions file, which is where all of the automatically generated assertions are put into by ALINT-PRO. So we can go ahead and open up this file, and what we see over here are two categories. We have the ND flip-flop properties, which are the exact same properties as mentioned before, just saying that the flip-flop value cannot glitch, and it has to be stable for a certain amount of time. In this case, we have it set for 2 clock cycles. Now, this second category here is the Mux and Enable synchronizer properties, and this additional property is essentially just saying that the signal needs to be stable whenever the enable signal is on. Or in other words, when you're transferring data, your signal cannot change. So, all that's saying is each of these individual data signals cannot change while the ready signal is currently active or on. So, now that we've taken a look at the CDC assertions, we can go ahead and look at Riviera-PRO simulation to see what's going on over there. So, over here in Riviera-PRO, we have a few different things. First, at the top middle, we have our simulation waveform. And so what we can see is that this simulation has our two different clock domains, as well as the ready signal and the data passing from one to the other. Now, before we get into the details, we will take a quick look at the test bench to just get an idea of what's going on. These parameters are exactly as they were in the previous video, our 2 clock half periods, whichever one is the slower versus the faster clock, how many stable cycles per clock we're going to want, and then this is going to measure how many cycles you need in order to have a stable signal between data changes. And then we just have a set of our internal, or rather our device under test signals, and then we have the test bench signals, as well as our 2 instantiations for the device under the test and the CDC assertions, a few initializations for some of the internal signals, 2 clock generators for the input, the transmitting, and the output, the receiving. And then we have a few extra things down below. So first we have the ready signal, which depends on a few things, including what the current count value is, which is just constantly incrementing, as well as the parameter defined up top, which is how many cycles we want per data change. And so this DN ready is only going to be ready once our value of count is going to be stable. And in the always FF block here, we just have the data input changing whenever we have the count value go up to a specific modulus. And finally, down at the bottom, we have a block just to check if we've reached a certain maximum value for our count. So here, if we've reached hex FFF, then we end the simulation. Most of the other test benches will be of this similar format, with maybe just a few differences. And so now that we've taken a look at that, we can go ahead and open up our waveform and compare that to our CDC assertions. So over here on the right, we see our CDC assertions. Now you'll notice that at the moment, the assertions are listed as having no data, and that's because our cursor is not placed at the end of the simulation. So if we were to place our cursor at the end of the simulation, so you'll notice that now that the cursor is placed at the end, we can see all of our finished assertions. And so here over on the right, we see how many times each assertion was tested during the simulation, as well as how many times that it passed and failed. Again, this is very similar to what we talked about during the last video. And so we can go ahead and see that these are the 6 assertions we're dealing with. 4 of them are for making sure the data itself is stable whenever the enable signal is on, and then the other 2 are just regular ND flip-flop assertion signals. So we've gone ahead and verified using this dynamic CDC verification that our synchronizer design works as intended and does not violate any of our assertions. So now that we've gone ahead and finished with the multiplexer synchronizer, we can go ahead and close out Riviera-PRO, and we don't need to save this file. We can go ahead and clear out our script results, close the CDC assertions, and then we can go ahead and begin with the second design that we'll be talking about. So this next design we'll be talking about is going to be the enable synchronizer. So what I'll do is I'll go ahead and set this as our active project, and we'll go through the exact same steps as before. So we have the script. Go ahead and change this to enable sync. And while this is running, we can go ahead and take a look at the enable synchronizer CDC assertions. So for the CDC assertions, we can see the exact same ND flip-flop properties as we saw for the multiplexer synchronizer, as well as the same stability properties that we discussed before. And that's because the multiplexer synchronizer and the enable synchronizer behave very similarly and can be implemented as the exact same set of hardware. So if we go ahead and take a look at the Riviera-PRO simulation, we can go ahead and see what the differences are. So first, I'll go ahead and open up my test bench, and that's for the multiplexer synchronizer, and then for the enable synchronizer. And what you'll notice is that these are actually both identical. There is no difference between these two. If I take a look at the bottom parts, they are also identical. And that's because, again, these two sets of hardware, these two synchronizers, can be implemented nearly identically, and so there doesn't need to be a difference in the test benches. So we'll go ahead and close the multiplexer synchronizer test bench, and we can take a look at the waveform here as well as the assertions. As you'll notice, the assertions are again all checked out, and none of them have resulted in any failures. That's designated by the failure counts over here. So we haven't run into any glitches. All of the signals have been stable for every single data point, so for all of the bits 0, 1, 2, and 3. So what we can also do briefly before we move on is we can take a look at the actual waveform produced by the simulation just to see what it looks like. So over here we have the transmitting domain, which is going to be clock A, and the signals that pertain to that particular domain. So we have clock A, we have the ready signal, as well as the data coming through. So that's these two. And then finally, we have the clock B domain, which is going to be receiving the data from clock A domain. So that has its own clock B data, as well as the ready signal, which is being synchronized, and the data coming out. Now what we can do is we can go ahead and zoom in just a bit further, and we can take a look at these ready signals from the perspective of both clock domains. So you'll notice that the DN ready gets asserted here and here. And during this interval, it's very important that the data of clock A that's being sent over to clock B is not changing in the slightest. And so what we can see is that over here, the synchronized ready signal occurs during this region. And during that region, we have to make sure that the data from clock A is unchanging. And you'll notice whenever the ready synchronized signal is on, the data from clock A is always steady. And so that's a very important part of the synchronizer, and we want to make sure that it's always going to be stable. There will be no glitches and no changes. And so that is the same for all of the rest of this simulation. Whenever this synchronized ready signal is on, the data from clock A is always going to be stable no matter what. And that's also indicated by the assertions down here, which confirm that we have no failures so far. So now that we've finished taking a look at our waveform, we can go ahead and close up Riviera-PRO. Now that we've returned to ALINT-PRO, I'll go ahead and close out this tab and clear out our terminal. And then we can go ahead and begin with our next synchronizer design. The next synchronizer we'll be talking about is going to be the Handshake Synchronizer. So again, I'll go ahead and set this as our active project. And then I can go ahead and run the run me sim script. And while that's loading up, we can go ahead and take a look at the CDC assertions. So we can see these CDC assertions here. So again, we have the ND flip-flop properties, which we've talked about before. And for this one, there are 4 different properties we need to make sure that we don't violate. So for the 2 signals, the acknowledge synchronized signal and the request synchronized signal, we need to make sure there are no glitches and that it remains stable during the receiving clock's period. So for the case of the acknowledge signal, that's going to be with respect to the receiving clock A, and for the request signal, that's going to be with respect to the receiving clock B. So you'll notice that each of these here is going to take a look at the state of our FSM within the Handshake Synchronizer. So if we were to take a look back at that very quickly, that's within this FSM module, and more broadly, if we look at the test.sv, we have the 2 different FSMs here. So the states of each of these are going to be what is checked for those assertions. And second, we have the Handshake Synchronizer properties, which we haven't seen before. So we have 2 different ones, the HS protocol and the data stability. The data stability is pretty manageable. So here it's just saying we need each of these data signals to be stable with respect to the receiving clock. In this case, we have clock B. The protocol essentially dictates that when one of our signals is on, say for example the request, it must remain on until it's been acknowledged. So request has to stay on until acknowledge goes on, and then the acknowledge would need to go on until the request goes on. And that's essentially what these 2 different lines here are using for their assertions. So with that out of the way, now we can go ahead and look at the Riviera-PRO simulation. And so now over here in the simulation, we see that we have a slightly different example than what we're used to. Namely, in this example, we actually are able to see what it looks like when we have some sort of assertion failure. Namely, these assertions pop up in red, and they also pop up over in the console with details about where the assertion has failed, as well as which assertion it is that has been violated. So for example, if we were to double click on this first line, that would take us to our CDC assertions page, and it would highlight the exact assertion that has been violated. And if we were to go over to the actual waveform view, and we were to zoom into this time, which is in this case 147 to 155, we can go ahead and take a look. And as should be pretty visible here, the state, which is the request signal from clock A, does indeed seem to be glitching during its cycle. You'll notice we have a few glitches here, and in this region, as well as over here. And this seems to continue on in a repeating pattern over and over and over again, which is why we saw that we had so many failure accounts for both the request glitch and the request stable. And so we can take a look at that one more time. So again, here we can see that the stability and glitch of the request signal are the only 2 assertions which have failed, while the rest have all succeeded, and it's due to those glitches that we saw in the waveform. Now, if we wanted to, we could go back to the beginning of the waveform just to get an idea of how this FSM design works, and in general, the synchronizer, the Handshake Synchronizer as a whole. So here at the beginning, we can go ahead and take a look at this request signal first. And this request signal is essentially indicating that we want to transmit data. And so after that request signal has been on for a certain amount of time, the receiving domain will be able to see that there's a request, get ready for it, and then actually read in the data while it's still stable. So here, for example, on this clock edge of clock B, we have that it's received the request signal, and that now it's going to actually read in from the data input of clock A over to the domain of clock B in D out. The same thing transpires over here in when we're reading the D in, which is a data of 2, and for 3, and so on. And that's the basic idea of this. We request, wait for the request to be acknowledged, and then read in the data, and then we keep repeating that same exact process. So we can go ahead and close up Riviera-PRO. We'll go ahead and close up the CDC assertions, and we'll also clear our terminal. So now we can go ahead and begin with our next design. The next project is going to be the Fifo Synchronizer. So we'll go ahead and set that as the active project and begin compiling it using our script. And we'll also take a look at the CDC assertions file. So in this CDC assertions file, you'll notice we only have ND flip-flop and wide ND flip-flop properties that we need to satisfy. The only difference between this and some of the previous examples is that we have a lot more signals to check with assertions. In particular, we have the two sets of signals that are 5 bits wide being sent from one of the Fifo modules to another Fifo module. That's these big blocks, essentially saying that each individual signal bit cannot glitch and has to be stable for a given period of time. And we also have the wide parameter, which just dictates that we can only have a 1-bit change at a time. That's those two right there. And finally, we also have this signal right here. These should go down below with the other 8 down here to group up with the total 5 bits. But other than that, these are identical CDC assertions to what we've seen previously. So we can go ahead and take a look at Riviera-PRO now. Here in Riviera-PRO, we can see our simulation has finished. We could also zoom in just a bit to see where it starts. And we could also take a look at the assertions down below. Now, first, to take a look at those assertions, I'm going to go ahead and zoom all the way over to the rightmost spot. And when I hover over this, you'll notice that every single one of our assertions has been successfully checked, and we haven't run into any failures. We could also take a look at the list of assertions if there were any failures over in the console window, but there aren't in this case, as there were in the Handshake synchronizer. So, now that we've looked at those assertions, we can go and just very quickly go to the beginning of the simulation waveform, just to take a look at how the Fifo synchronizer behaves. So, to go ahead and start off, each of these lines here for the two enable signals dictate when each of the Fifo blocks are told that they can either read or write to or from the memory. Specifically, I have it set so that each of the enables goes off one right after the next, just in this pattern. So it's not like multiple consecutive reads or multiple consecutive writes, just one after another. Additionally, each of the Fifo blocks starts with their pointers at 00, which is the first address in the RAM, and then they go up from there. In particular, each of these pointers is going to count in gray code. So here we start with 0, 1, 3, 2, 6, 7, 5, etc. And that's counting in gray code, which means only 1 bit changes. Additionally, we can also take a look at the data that's being read and written. So W here is the write data. So the write data is essentially just going to be whatever the data is that W pointer is writing to the memory, and read data is whatever R pointer reads from the memory. And so you can see that after we do a few writes, we write 0, it reads 0, we write 1, it reads 1, we write 2, it reads 2, and this pattern continues for quite a while. There's also some more signals added on to this waveform, something like the empty underscore full here, which either represents if the memory is full or if it is empty. In the case of the R pointer, it represents whether or not the RAM is empty, and in the case of the write pointer, it represents whether or not the RAM is full. Here you'll notice the RAM is never full because we never allow multiple consecutive writes in this particular test bench. However, we do occasionally have the RAM emptied because after a write and then a consecutive read, there is nothing left within the RAM. Additionally, we can see more details about what the memory specifically is encountering. For example, there is an enable signal for the memory, as well as what addresses are being used for the write and the read functionality, as well as additionally the full signal to ensure that no writes occur when it's full. And beyond that, all of this waveform will behave similarly to how I've described it for the rest of the simulation time. So with that done, we can now go ahead and close out Riviera-PRO. And then we'll go ahead and close out the CDC assertions and clear out this view. That's it for this video. Thank you for watching.